So, the second part of basic segmentation. So, it is kind of a segmentation problem is kind of a machine learning task. You have to be able to do it automated, you have to tell in some sense what classes you work with. And looking at this case, you have images from electron microscopy, and some features here, the mitochondria, is what you want to identify. And it's not so easy actually to distinguish them from just the gray level, as we will see soon. This is the mask that someone has been sitting down and marking out the regions, which are the relevant ones. And that is usually done by hand painting in some sense, or by some pre-segmentation tool. So in principle, what we want to do is to identify which pixel belongs to foreground and which pixels belong to background. And that can be done as we have in this image, we have some true positives and true negatives. Those are the ones we want. True positive is the foreground, so mitochondria, and true negative is everything else. The false positive are values outside of the mitochondria that are marked as mitochondria. So a misclassification. And false negative are mitochondria pixels that are labeled as background. And now we can see what happens when we apply a threshold to this. So we have the image, and now we take the histogram, place a threshold somewhere, and this is what we get. So a lot of misclassification. There's a lot of false positives and a lot of false negatives. And considering this is what we want, this is not very close to what you really want. So we need to do something else. We can look here at the matrix where we look at the true negative, false positive, false negative, and true positive. So based on the mask we already have, we can separate out which is what. And here we can also see the counts of each one. So this is in principle the confusion matrix, but done with the images. And metrics that we want to work with now is precision and recall. So recall is sensitivity, and that's the true positives over all pixels that have been labeled as positive. And the other one is the precision, the way we have the, so I should actually have added that as a list. But anyway, so we have the true positive over the true positive plus the false positive. And here was the false negative. Together, they can be represented in the ROC curve. And then we can see here, by the way, that we have a recall of 82% and a precision of 18%. So not so fantastic. So this would be also information that we can use the confusion matrix for, and that one you saw already last week. And the other way would be to use the ROC curve, which is something that was in the beginning developed in for radar applications. So actually already during World War II, when they started seeing the blips on the radar screen, they needed some way to measure or to tell how many false positives and how many false negatives and true positives, etc. So what we can see is that for a single threshold, we can compute this curve, and then we can take the values out here. You can see out of the curve, out of this table, from this data that we had, you can see some information about how the recall and precision is. What we do in the RRC curve is actually to look at the true positive rate and the false positive rate, and those are plotted against each other. And that can be done automatically, more or less, with help of tools in the Python toolboxes. And if we have a single point that we used, then we only get this one, and behind the legend we have the ideal that we should have false positive should be 0, and the true positive should be 1. That is the ideal case. But in this case we have false positive around, what is it, 35, and a true positive around 82. And running on, then we can see, if we try with different thresholds, we can see how the curve is plotted. If we just would do a random guess, that would be a straight line in this context. Ideally, we want to have something that goes up here and just keeps constant on the top. Now there are different ways to improve the performance of the RRC, to see different RRC curves and improve the performance of the segmentation. And for that we apply different filters to the data. So we have the raw data, we have a Gaussian filter which takes out some of the noise. We have the difference of Gaussian, two Gaussians. So in this case we're talking about a Gaussian of sigma 1 and a Gaussian minus a Gaussian of sigma 3. So it's a kind of a bandpass filter. And what we get out is more edge information. Or we can do a medium filter, which would produce something that looks like a little bit the Gaussian one. And now we can see what happens with the RRC curves with those. This should continue here. Yeah, there it comes. And now we can see what the RRC curves are for different filter techniques. The difference of Gaussian is not very promising. As you can see, it even is sometimes worse than random guess. So not a good idea. Then sometimes it goes up a little bit. And it appears that the best segmentation performance we get in this case using the Gaussian filter. So ways to compare which is the best of these curves. What is our metric to determine if this is a good or bad one? And typically what is used is the area under these RRC curves that gives us a quantitative value on how good the performance is of a segmenter. So looking at that, we can see that for our three different filters, we have no filter, which comes up to a little bit less than 80%. The Gaussian brings an area of 85-ish. Difference of Gaussian is about a little bit more than 50%. And the median filter is slightly somewhere between the Gaussian and the no filter at all. So this gives us an idea how good our different filters are, what they do for the segmentation. Then there are some slides here about evaluating models. In principle, what is about is that you set up different frameworks, as I already showed in the enhancement lecture. In the end, the smoke test that I used there, that you have a procedure where you go through different parameters and see how they perform and produce different curves, RRC curves, which then can be evaluated and compared between themselves. Then a next problem is that it's not always we have a single class in the data, but we can have different things. In this case, we have a data set of a shale, some data that was acquired at the synchrotron at SLS. And now we have not only stones and voids, but we also have something in between. And here's one image out of it. And we want to see 3 different classes. And the problem with 3 classes is one, that the histogram may look like this. Well, I wouldn't guess that there are 3 classes within this histogram. And that's always the problem, that the histogram is usually too much between the classes, and there is a lot of class overlap, and that in turn results in a lot of misclassifications. And oops, that one didn't appear well. So what we need to do is to segment this one into voids, clay, and rock. And with linear thresholds between them, we have selected 3 bands here. And then we can see something like this. There we have the 3 classes, but there is always a problem when you have these 3 classes, that if it goes from one to another, in particular from rock to void, then you often have, if you look at the edge, so you would have an edge looking something like this, and you have the threshold here, which is 0.3, and you have a threshold here, which is 0.5. But the problem is you have maybe a couple of pixels in between here, and these pixels, they are classified as clay. So it would look like each grain has like a coating of clay around it. And I even seen papers where people are making interesting hypotheses about film coatings around stuff, which is essentially only an effect of misclassification. So please be careful when you start doing multi-class segmentation, not to interpret too much into films. And it gets even worse when people start using very creative color maps. Then you can get nightmares when you see it. It's really bad what can appear out there. So, it's not easy to get these, but there are, of course, methods. I'm not showing them here today, but there are methods how you can come around this problem. One is in particular that you can use the gradient information to see if there is something or not. And how to implement these in different languages. Segmentation is very easy to begin with. You can have a threshold image, then you just say the NumPy array or MATLAB matrix is less or greater than a scalar, a threshold. Or you can combine them also in a more complicated thing if you have multi-class segmentation. You can also use some mapping function using lambda functions, a little bit more fancy in Python, but usually I think it's sufficient to use this one, but sometimes it can make sense to use this more fancy approach. Java, then you write a couple of nested loops, going through the data. And same you do in C++, but in principle this is now done with loops for each axis. But as you may have seen already in the exercises, there is this ravel function which takes the whole multidimensional image and makes it as a long line. You can do the same in Java and C++, and that's actually what I'm personally doing also. It's rarely I need the coordinate information, and then it's just unnecessary to start using this information in the loops. Sometimes it's relevant to use it, then you have to do the many loops, but otherwise it's just one long one. So, I'm not going to talk more about segmentation today, but I'm going to switch the topic to morphology, and that's actually a way to get rid of the misclassified pixels. And it's a set of operators that are very useful, and in principle in black and white images it's just kind of a majority counting, and that in a neighborhood around the center pixels. And here you can see the effect. We have the cross again, which you saw before, and with a simple thresholding this very noisy image turns into this, which is, well, with some imagination you can say that it's a cross, but there's a lot of misclassified pixels in it. And to get rid of that we need some operation. Oops, wrong way. So first of all, the morphological operations, they work in a neighborhood. So with the convolution I was talking about kernels. In morphology it's more about neighborhood, so you look at the neighbors of a single pixel, and then you can see what's happening there, and then you count the pixels that fulfill, that match some kind of mask. And you can use morphology for many things. The basic things is this misclassified pixel filtering, but you can also do other morphological operations. You can do component labeling, you can do distance maps, and with that you can do a very interesting analysis too. So for example, component labeling is about putting individual labels on different items in the image, or index numbers actually. So it splits the image into different regions. Doesn't tell what it is, but it knows that they are different. They're not belonging to each other. So in 2D we are talking about two different neighborhoods, 4 and 8 connected. And actually I think I should go back a little bit. No, now I'm going the wrong way. So for the 4 connected case, then you have the center pixel. No, so then you have the center pixel, and then you look at the pixel above it, to the right, to the left, and below it. So that is the 4 connected neighborhood. If you have 8 connected, you probably can guess. Then you have this, this, this. That's the center point. And then you have 8 neighbors around the pixel itself. And these are then compared during the algorithms. You can use other masks in the operations, but these are the basic neighborhoods that we define many algorithms around. And here you can see what is the effect when you apply different masks. Let's see. Yes. So we have here, we have disk 5 by 5. This is the discrete representation of a circle in a 5 by 5 neighborhood. If you do it a disk 7 by 7, it looks like this. Disk 11 by 11 looks like this. Starts maybe to look something like a circle, but still not really. And then we have other neighborhoods or different masks where we have cross 5, 5, 7, 7, 11. And lines can also be used, and all these can be used as different patterns or structure elements when you do the morphological operations. For the basic cleaning, we usually only use the disks, but if you want to already put in some information about structures they are looking for example, if you're looking for lines, it surely makes sense to use the line objects. The octagon is almost a circle. And now with that we have the basic information around how to work with the different operations. So we have two basic operations. That they are erosion and dilation. So in principle, if any voxel in the neighborhood, the erosion is shrinking the object. So if you take the structure element, whichever you select, if any voxel in the neighborhood is 0, then you take away the central object, central pixel. On the other hand, if any object is in the dilation case, if any in the neighborhood is a 1, then the central pixel is also set to 1. And that gives you a region growing effect. And here you can see some basic example. Let's see. That's just the code, so let's go for the example here. Here I have an original image, and I applied dilation to this one. And what's happening now is it's dilation using cross. So it's a disk disk in a 3x3 neighborhood, or also could be called a cross. So looking at this pixel out in the corner, you see that it's connected with those two. So if you would look at this one and you have a 1, then you would paint in here, and then you can see that the whole structure is growing up. So this would be the result of a dilation. The erosion goes the other way around, so it shrinks the information. So if there are places without 1s, they are deleted. So the only thing that remains is this yellow region here, and after erosion there is not very much left of this structure. So these are very thin structures actually, so they are much eroded. But erosion and dilation itself, it actually changed the shape a lot, and it's not always what we want. I mean, then you would get, for example, a different volume measurement. You would also get different surface area. You would lose information. So usually what we want to do is instead to use the operations opening and closing, which is a sequence of, in the case of opening, a sequence of erosion and dilation. So first you shrink, and then you let it grow back again. The purpose of that is that you would actually take out single misclassified pixels in the background. So those that were false positives, they would be removed, but the main structures, they would be intact. Closing goes the other way around. So if you have false negatives within the sample, then those would be removed by closing operation, because that is first dilating. So if there would be a hole within the object, the dilation would close the hole, but you would grow the whole thing, and then you'd erode to get back to the original shape. And here you have an example of closing. So we have this structure again with these holes in it. So the first step is to do the dilation, which grows out into this shaded blue area. And then after that we do the erosion, and what remains are these greenish blue areas here, and the closed structure is what you can see here. So these two holes, they are closed. Also the gap between this one and that one, they are also closed. So in the end what you have is almost a fully connected structure. And these are very useful operations that are used a lot when you have done different segmentation tasks. Problems with the segmentation is that you have partial volume effects. So the resolution of the system is not able to capture all the information. For example, if you have very small holes, they appear as very weak features in the image, and they may be classified as solid, but they would be gaps. And that is the problem when you come into the partial volume. And also around the edges, there are edge positions that are not really filling out the whole pixel, and they appear as less intense in the data, and they will also be misclassified. Another thing is how well your data is representing what you actually want to. And one question here is when a sphere is really a sphere. So depending on different radius, you have different representations of a sphere. If you have radius 1, you get this three-dimensional cross. Well, you can say it's kind of a sphere, but not really. And then you have to go up pretty much until it starts looking like a sphere at all. And what I did here is to calculate what is the volume error compared to the analytical sphere for different radius. And you can see that you need to go up to radius about 10 to get down to 1% error in the volume representation when you have a discrete sphere. And then of course it goes down rapidly to smaller sizes. But you need pretty big objects to really represent them well. And that's also something that you need to be aware of when you select resolution and pixel sizes for your imaging task. Yeah, and here you can see also the case of partial volume effect. So if you have a smooth object, then you can get some wrong segmentations also if you have different sizes. And you can see here the volume fraction of this whole image is 32%, and when you have 20 pixels, so smaller pixels, then you go to 40%. And at some point it levels out, so towards 45% when you have very large images. So it's important to have sufficient pixels to represent objects well when you segment them. Otherwise you may make the wrong conclusions from the data. Another effect is when you do rescaling. Also be careful again if you scale a 500 by 500 image down to 15 by 15, which is sometimes relevant if you do machine learning. You don't want to work with too large patches because you will blow the memory completely, and also time-wise it takes very long time. So it's a very common approach to downsample the images more and more, but also then you will get these partial volume effects. And here is an example of that, where you do the downsampling. Again, we have the nice case with 500 pixels. We have very nice sharp edges. Then you do the downsampling, and you can see already here that all of a sudden you get intermediate values on the edges. And those are represented around here, for example. And you can see in this area here, there is a gray pixel, and that is a partial volume effect from the downsampling. Same you can see on this one, and that actually also corresponds to this value. It's a little bit brighter, so you can see it's also higher up. This one is pretty dark. Also here you have some, and on the last one, well, there nothing appeared, but it could also possibly happen. And that was the end of it. Otherwise, in segmentation, I could actually talk a little bit more about the case. Let's see. This is a slide I will bring up on the web page afterwards. But let's see. It must be in here. Yes. So I was also talking about the multi-class segmentation before. I can go a little bit more on detail on that. Yes. So we can use different approaches when we want to work with multiple classes. I haven't talked about algorithms yet, so this is from a different lecture with some pre-information, but I can at least show you some, let's see. Yeah, here we have a nice example of the multi-class segmentation. And as you can see here, we have this histogram. It's actually pretty nice separated classes, but still you have the problems that you have some gray levels that span and that change in the band here between the segmentations. And here you can also see it as a film around. I made this model so that it should be high intensity to low intensity, but thanks to the unsharpness in the image, we get this smooth transition. And the segmentation, well, it's tricked out completely, and you get here some film around the object. And that is the one I tried to draw before. And here you also have several pixels within this band, which is ambiguous because we don't know if it's actually belonging to the class or if it's not. And one trick to get rid of that is to use, it's not in this slide. Was not meant to be. No. So, somehow my computer doesn't want to talk to me anymore. No, I didn't have that here. Okay. Nope. So anyway, that was a little try to show you something, but I should have taken a different PDF for that. If you want to look more on segmentation, the basic stuff, I also have my other lectures from this fall. But that would be, if you go on the web page. Oops. So I also have the MNT lectures from the previous fall. There you can also see some slides on the segmentation. And I think on this one I have the example I wanted to show you. Yeah, here it is. Yes. So what you can do is to use the gradient to guide you around these tricky cases. So you can use the gradient information as kind of a guard when you are around the edges. So the gradient tells you, okay, here is a lot of happening, so please pay attention. And with the help of this edge guard, we can get rid of this problem with the film. So that is a trick you can use without going too much into automated methods. Well, that was it for today. We have new exercises to play with, some fossil data and nerves. and you can play with that. And there is also from previous years, there are some information, some other exercises using KNIME or even Kaggle competitions that you can play with for segmentation. But the main things, they are the first two, and they are on their website. So, thank you for today.